Let us next solve this exercise. Exercise 4. Here we have to state and prove a version of theorem 1151 for the Riemann-Stieltjes integral. We have already seen this theorem for Riemann integral, and it is that theorem which tells us that a uniformly continuous function on a bounded interval is Riemann integrable. Now we need to state a similar one for the Riemann-Stieltjes integral and prove it. Now before we do that, we are going to need some similar versions of a few other results about integration, Riemann integration. So let us start with them and let's make them a part of the solution itself. Accordingly, we start the solution like this. We will need the following versions of some previous results on Riemann integration. That's understood. And the first one we are going to need is this. Let me give this a name also. Let me call it lemma 1133 star. It is the Riemann-Stieltjes integral version of original lemma 1133. That's why I decided to identify it like this. And the statement is this: let I closure be a subset of X and X be a subset of R, where I is a bounded interval. Okay. Next, let M be a positive real number. Next, let alpha from X to R and F from I to R be functions such that alpha is monotonically increasing and the function f satisfies these inequalities. Let me write it here. Minus m is less than or equal to f of x, which is less than or equal to m for all x in the domain of f, that is for all x in I. Then minus m times the alpha length of I is less than or equal to the lower Riemann-Stieltjes integral of f with respect to alpha, which is less than or equal to the corresponding upper integral of f, Riemann-Stieltjes integral with respect to alpha, which in turn is less than or equal to m times the alpha length of I. In the Riemann integral version, in place of alpha length, you have ordinary length. That is the difference. Now, how to prove this? The proof actually is very easy. The proof is exactly similar to that of the original lemma. Wherever you see ordinary length, you replace that length of that interval, whatever interval you are considering, by the alpha length. That's it, that will give you the proof. Okay, so we now have this lemma with us. Then there is another one that we are going to need. Okay, yeah, luckily I can modify this one itself, and this is the corresponding version of lemma 11.3.11. In this one, the beginning is same. We still have these containments. I is a bounded interval whose closure is contained in X and X is some subset of R. We also have, but we do not, however, have this. This is not needed any longer. We still have, of course, our function f and alpha, where alpha is monotonically increasing and f is bounded. Here boundedness of f comes from this statement itself, but now we do not have m, we are not saying what bound we are considering for the f values, but f is bounded. So let me continue from here, and f is bounded. Also there are other ingredients. Let h from I to R and g from two more functions are there. G from I to R, B, PC. Okay, PC means piecewise constant functions WRT with respect to the partition, some partition P of the interval I. Okay, so all these things are the hypothesis. Then what is the conclusion? Oh, sorry, I forgot to say one crucial thing. No, it's not the entire hypothesis, such that, how are the functions related to f? Such that h of x is less than or equal to f of x, which is less than or equal to g of x for all x belonging to I. That means h and g are piecewise constant. H minorizes f and g majorizes f on the interval I. Now we have everything. Then the PC integral of, let me first write the one for G. PC integral, Riemann-Stieltjes integral with respect to I is greater than or equal to something, some symbol I am going to write, which I will define. F u of fp alpha. This looks like upper Riemann sum, but if you want, you can call it upper Riemann-Stieltjes sum, and it is defined similarly. The only difference here is that instead of ordinary length, we have alpha length now. This is greater than or equal to this, which by definition is this sum. Summation. The summation has terms corresponding to the subintervals j in the partition P such that j is not empty. And what are the terms? Supremum of f of x as x varies over j. So far it just looks like ordinary Riemann's upper Riemann sum, but now in place of ordinary length you write alpha length of j. That is the difference. And the PC integral of the minorizing function with respect to alpha is less than or not less than or equal to. Is it less than or equal to? Am I getting it right? Let me just see. Suddenly I got a little bit confused. This is greater than or equal to upper, yeah, because these things approximate our thing more nicely than these integrals. Yes, yeah, okay. So this will be less than or equal to the corresponding lower Riemann-Stieltjes sum. I am not sure if this is a technical term, Riemann-Stieltjes sum, but we can call it, okay, to remember it. And this one is similarly defined to be this sum. Here, in place of supremum, you will have infimum. X varies over j times the alpha length of j. Okay, so this is that result. But it's Riemann-Stieltjes integral version. Do you remember why we need this j to be non-empty here? Because if j is empty, then this is after all the supremum of a set, right? What is the set? The set is all the f values as the input varies over j. If j is empty, that set itself is empty. And by definition, then its supremum will be minus infinity. That we do not want. That is why we require j to be non-empty. Similarly here also. Okay, now why do we need this result? Where are we going to need it? We actually need it to prove a Riemann-Stieltjes version of another result, which in turn we are going to need in our proof, namely the next one. Oh, I did not say how one can prove this. To prove this, you can guess that this is also going to be something which only needs minor modification. I mean, you just go to the proof of the original lemma, and there you just change the references of lengths by ordinary lengths by alpha length, and wherever you see ordinary upper Riemann sum u f comma p, you replace that with these quantities. Wherever you see L f comma p, you replace that with this. More specifically, to prove this, see the solution. To exercise 11.3.4. This is where we proved the original lemma, lemma 11.3.11. And now finally, let us see proposition 11.3.12, its Riemann-Stieltjes integral version. This time we have to again repeat the conditions, there is no other choice. So the beginning is again same, let these containments be there where I is a bounded interval. Let alpha from x to r and f from I to r be functions such that alpha is monotonically increasing. And f is bounded. Okay, so here we have only this much. Then the upper Riemann-Stieltjes integral of f with respect to alpha over I is equal to the infimum of the set of all these upper Riemann-Stieltjes sum as p varies over the possible partitions of I. P is a partition of I. The corresponding statement for ordinary Riemann integral involves ordinary upper integral and ordinary upper sum. That's it. And similarly, the lower Riemann-Stieltjes integral of f with respect to alpha over I is the supremum of the set of all lower Riemann-Stieltjes sum as the partitions vary. And to prove this, again, it's very easy. Oh, I did not write the reference here. So I don't exactly know in which exercise it is also an exercise. And I'm suspecting that this is going to be exercise 11.3.5. So on that guess I am going to write this. So it may be something else, okay, so you just check. To prove this, see the solution to exercise 11.3.5, because I remember somewhat that after exercise 11.3.4 we proved this one. This one means the original Riemann version. Okay, so now we have these results, and now we can state the Riemann-Stieltjes version of our actual thing, theorem 11.5.1. Accordingly, according to how we are naming these things, let me call this theorem 11.5.1 star. Alright. And this is the statement. Let these containments be true where and one more thing. When I say to prove this, see the solution to exercise 11.3.5 and such things, I am not making it up, okay. I have actually gone through the details and I have convinced myself that yes, it works. But I urge you to do the same for yourself and see that yes, it really works. Where I is a bounded interval, let alpha from x into r and f from I into r be functions such that alpha is monotonically increasing and f is no, ordinary boundedness is not the thing here. F is uniformly continuous. Yeah. On I. Okay, alpha as usual is monotonically increasing, but f this time is uniformly continuous on I. Then f is Riemann-Stieltjes integral. You may or may not hear some firecrackers in the background. Okay, so if you do, I'm sorry about that, but it's beyond my control. It's going on. At any time of day and especially at night, this just goes on. With respect to alpha over I. Okay, now we come to the proof of this. Actually, the proof is similar, but this time we are going to say something. So let me also write proof, although we won't write all the details. So what do we want? We want to show this, that the lower Riemann-Stieltjes integral of f is equal to its upper Riemann-Stieltjes integral. That's what Riemann-Stieltjes integrability means. Now, in the original proof, First of all, the case where I is a degenerate interval has been considered and it has been tackled. Okay, so in that case, both these integrals become 0, just like the ordinary Riemann integrals become 0, upper and lower, when I is degenerate means actually empty. That case has been considered in the text also. Here also the integrals become 0. Let us first write that. If I is empty, then both the integrals equals 0 and we are done. Can we take a moment to see why they are 0? For example, let us see why the lower Riemann-Stieltjes integral is 0. Okay, so this is where we just do a kind of rough work, means it's for our own understanding. It need not be a part of the proof because it is something very easy. If I is empty, what is the status of f? F now looks like this. That means f is the empty function with range R. What type of function is what type of function is f? Is f a constant function? Is it piecewise constant? Yes, actually f is constant. How do we show that f is constant? What is the condition for a function to be a constant function? The condition is that there exists a real number C such that the following implication is true, that if x belongs to the domain of the function, then f of x is C. At every input the output is C, then only we call it constant. This is an implication whose hypothesis is true. Conclusion is something, okay, or antecedent and precedent, if you call them that. This is, hypothesis is not true, hypothesis is false. The beginning is false, so the implication is vacuously true, but it's true nonetheless. That means, yes, this is a constant function, and the strange thing is that this is true for any real number C. So although it is constant, but there is no specific value of C, but it's constant. Okay. Now, if one goes for calculating the lower Riemann-Stieltjes integral from definition, then what would one do? See, the lower integral involves what? Minorizing piecewise constant functions. You have to consider a function h like this, which is piecewise constant and minorizes f, that is h of x must be less than or equal to f of x for all x belonging to the domain. Note that our h also is empty function. Actually h is equal to f because there can be only one empty function with a given range. Just now we have seen that f is constant and so piecewise constant and so is h. Also, this condition, this inequality is true again vacuously. And what about the PC integral of H? What can you say about this? See, by definition, it is Hj. By Hj, I mean the constant value of H on the subinterval j times the alpha length of j, as j varies over P, where P is a partition of the empty set with respect to which H is piecewise constant. Now, what type of partition can you think of when the interval itself is empty? There are two choices. One of them is this. There are two choices for P. P can either be empty or P can be this. Actually, we discussed this way before discussing these things when we were familiarizing ourselves with partition for the first time. There itself we figured out that when we have the empty set as our interval, these are the only two partitions. Now, what happens to this sum when P is the empty set? In that case, this sum is the empty sum, and by properties of sums over finite sets, which we saw way back, this is 0. Okay, we actually proved that. So this will be 0 if P is this, because the sum itself is empty, there is no term. However, if P is this singleton set, then there is a term in this sum. The sum is not empty, but the only term corresponds to J equal to the empty set. Do not confuse this sum with that upper Riemann-Stieltjes sum where we need J to be non-empty. That is something else, okay. This is the integral, okay, PC integral definition. So here J just varies over P. J can be empty. So in this second case, J is just the empty set. So there is only one term, which is H empty set times alpha of empty set. We don't really know what H empty set is. In fact, it can be any C. But alpha of empty set by definition of alpha lengths is 0. So in that case also this is 0. So no matter what PC function you consider which minorizes f, its PC integral is 0. And so by definition of this lower Riemann-Stieltjes integral, what is the lower Riemann-Stieltjes integral? I need to write. This is the supremum. Here I am writing the definition, okay, not that proposition. H is piecewise constant on I and minorizes f on I. This set is the singleton set consisting of 0. Which is equal to 0. That is why the lower Riemann-Stieltjes integral is 0. Similarly, the upper Riemann-Stieltjes integral is also 0. And that's why we said that both the integrals are 0. So, we can now assume that I is non-empty. I may still be degenerate, having only one point, one real number in it, but I is non-empty. Now, because I is non-empty, there is at least one point in I, and that is why the partition cannot be empty. Also, there must be at least one subinterval in the partition which contains that point, and hence that subinterval itself must be non-empty. So, any partition of I has at least one non-empty subinterval. Now, if you go to the proof of the actual theorem 1151, you will see that there cases have been considered. That is, first, degenerate intervals have been considered separately, and then non-degenerate intervals have been considered. And you already know that when we consider non-degenerate, when we consider I to be non-degenerate, it can be of any of these four types. Where A and B are real numbers with A less than B. So, A and B are that, okay. And then we just mimic the original proof, the proof of theorem 1151, and adapt it to this situation. So, we are just going to see bits and parts of this. If alpha is constant, then also both the integrals are 0. A similar thing as this one, but here, however, I is like this. I mean, I is one of these, it has one of these four forms. So, I is non-degenerate, that we know. But even then, if alpha is constant, then both the integrals are 0. Again, if you argue like this, when you take a, let me just elaborate a little bit of how that is 0. This time, let me consider the upper Riemann-Stieltjes integral. The upper integral is, by definition, the infimum of PC integrals where G is PC and majorizes F, right? Now let's calculate this, okay? Suppose you take any such G and G is PC with respect to some partition P of I. Then the PC integral of G, Riemann-Stieltjes integral, will be equal to, by definition, summation Gj, which denotes the constant value that G has on the subinterval J, times alpha length of J as J varies over P. Okay. Now this J either is degenerate or non-degenerate. If J is degenerate, this alpha length by definition is 0. But if J is non-degenerative, J also looks like one of these, then its alpha length by definition will be alpha B minus alpha A. However, since alpha is constant, alpha B is equal to alpha A, so again it will be 0. Note one more thing, that the constant function is monotonically increasing. We are not saying that alpha is strictly monotonically increasing. We just need alpha to be monotonically increasing or not decreasing. Okay, so that way you get 0. And that way all these PC integrals are 0 again, and again we get back that same situation. So you get the singleton set 0, and so the upper Riemann-Stieltjes integral is 0. So we assume that alpha is not constant. These things actually are there in the book itself, because this is how the proof of the original result went. Alpha is not constant. So alpha of A and B are this A and B, okay, we are coming from I is one of these. Alpha A needs to be less than alpha of B. Alpha of A is already less than or equal to alpha of B due to the increasing nature of alpha. But if they are equal, then obviously all the other alpha values which are forced to lie between them will also be equal, making alpha constant. So that is why we need to have this strict inequality. Now choose epsilon greater than 0 and let delta be as before. Now what this be as before means, to know that you have to go back to the original proof and see how we chose delta there. Okay, so that is just, it will be simple repetition, so I am not writing that. Now by the Archimedean principle, there exists an integer, a positive integer n, an integer n greater than 0, such that k, which is b minus a divided by n, is less than delta. N can be chosen large enough, you already know these techniques, so that this becomes less than delta. Note also that the non-degenerate nature of I makes A, we have already mentioned that, okay, A is less than B, so this is a positive real number that is less than delta. Now partition I into n subintervals. Each of length k. And do you remember that depending on the type of the interval I, we said, or rather the author said, when we were proving the original result, how to handle these subintervals, that is, some slight changes have to be made. depending on whether I is a closed interval or an open interval. Nothing concrete is given in the book, but I think while going through the proof, while doing it here, I considered one of the cases and showed how it can be done. It's nothing really very difficult. Okay, so just like that, now also we can do it. All right. Now, oh, and one more thing. This, if you want, you can give this partition a name also. Let P be this partition. Now, by proposition, the proposition that we saw before stating this result, that is proposition 11.3 to what start. By that proposition, we have this. The upper Riemann-Stieltjes integral of f with respect to alpha over I is less than or equal to am I correct in writing that the upper Riemann-Stieltjes integral? Let me first write it and then I will justify. So what I have written is this. Supremum of f of x as x varies over ji times the alpha length of ji as I varies from 1 to n. What does this proposition say? It says that the upper integral is equal to the infimum of all the UFP alphas. This is also one of those UFP alphas. Because this is the infimum, this is after all a lower bound, so it will be less than or equal to any element in that set. One of those elements is this. And you can see actually what this is. Why? Because this is actually nothing but UFP alpha, where P is this. Because the subintervals involved here are the elements of P, that is why. So we have this. And similarly, from the other lower integral thing, so this is one of the inequalities, and the lower integral is, because that is the supremum, so that will be greater than or equal to the corresponding L, which is just this. This time we will have infimum times the alpha length of ji. Okay, so the upper integral minus lower integral will be less than or equal to summation supremum minus infimum x varies over ji, x varies over ji times the alpha length of ji as I varies from 1 to n. This stage also came in that original proof in the book, but where you have ordinary length here. And that's why, skipping the other details that come after this, we straight away write which are exactly the same, or you can say similar. So instead here I write with the rest of the argument as before. We have upper minus lower is less than or equal to epsilon times alpha length of I. Okay. Now since epsilon is arbitrary, you know what to do after this, and also this is greater than or equal to 0. Oh, by the way, where are we getting this from? This also needs a justification, right? This is where we use lemma 1133 star for this. Use lemma 1133 star. So we have actually used proposition 1132 because that's how we are getting these things, and in order to prove proposition 1132 star, we need lemma 11 star. So that's why we had that also, and the first star lemma is used here. Now the arbitrary nature of epsilon forces this to be not positive, but we have this also, so it must be 0, and that is how you have equality. And that is why f is Riemann-Stieltjes integral. The solution ends here. There is one more exercise that we will however do in the next analysis video, that is next Sunday. And tomorrow we again have number theory. So let me just end things here itself tonight. See you tomorrow with number theory. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.